Okay, welcome to Nano at Tech here at Georgia Tech, our seminar series from the Institute for Electronics and Nanotechnology. Before I introduce today's speaker, for those of us in the room and online, just a couple of announcements about some other upcoming events. So the next seminar in this series will be actually in 2 weeks, but instead of on our usual Tuesday, it'll be on Monday, October 25th. And the speaker will be Professor Saurabh Saha from Mechanical Engineering here at Georgia Tech. A couple of other events, both in person and online. So another symposium series that we have here at IEN is called Nano Fans, which is about connecting nanotechnology to the life sciences. And the next installment of that is actually tomorrow morning. If you want to sign up for that or find out more information, you can go to the IEN webpage. We also have the National Nanotechnology Coordinated Infrastructure has a webinar series, a monthly webinar series, and the next installment of that series will be on October 28th, 4 p.m. Eastern Time. And the speaker will be Kurt Peterson, who's a member of the Silicon Valley Band of Angels, who'll be talking about what investors are looking for in startup companies. And then finally, if you are here in more local, you can sign up still for the fall microfabrication short course, which will be held next week over the course of 3 days. And if you want, you can find out more information at the IEN website. So it's a real pleasure to have with us today for our Nano at Tech seminar, Professor Carlos Silva. Carlos got his bachelor's degree at Luther College and then his PhD in physics from the University of Minnesota, before going across to Cambridge to do a postdoc. He then started his academic career at the University of Montreal and then came to Georgia Tech in 2017, where he has a joint appointment in chemistry and biochemistry as well as physics, and a courtesy appointment in materials science and engineering. Among his other activities, he's an associate editor for Science Advances, and has achieved fellow status with the American Physical Society and the Royal Society of Chemistry, among other honors and awards. And so I will turn it over to Carlos.
Thank you very much, David, first of all, for the invitation. It's really a pleasure to talk at Georgia Tech. It's an environment that I've really appreciated very much, and to be presenting our work here is really a pleasure. And part of the seminar series, which is very, very important. First thing I want to say is, if people don't mind, I'm going to take my mask off. If people object, I will keep it on. But I prefer to talk without a mask, so if people object, I will put it back on. What I'm going to present today is a story that is very much a Georgia Tech story. It's a project that we basically started when we moved in 2017, and I will give you a summary of what we've achieved. This has been really a very exciting story that is ongoing. And in the title, you notice that it's different than in the announced title. The reason is our friends, the crystallographers, really appropriately object to us calling these materials perovskites. You'll see why. And so the proper name is our Ruddleston-Popper metal halides, rather jargon, but that's what I'm going to call them today. Before I do that, I want to start by acknowledging the team, because this is really the essence of the project. Here in the audience is Esteban Rojas, who is the current, I would say, the current champion of this project. He's following the steps of Felix Tuan, who was an outstanding PhD student as well, graduated pre-COVID, but intellectually, really the main source of intellectual input from this project is Ajay Srimath-Kandada. He was a Marie Curie International Fellow in my group and is now assistant professor at Wake Forest. Very importantly, a lot of these materials come from Milan, from the group of Ana Maria Petrozza. Really, Daniele Cortecchia is really, he has hands of gold. Everything he touches turns on gold, and the samples are very good. But a lot of the samples now come from Esteban, who has this amazing ability to be both a chemist and a physicist, and so he makes very good samples as well. But Stephanie contributed a lot to, not directly to what I will talk about. She spent a few months in our lab as a visiting student, and Giulia Folpini is Ajay's student, who also, I don't think I'll get to her work, just in a contextual way, but she's very much acknowledged. There are theoretical collaborations from the University of Houston, from the University of Mons, from Los Alamos National Lab, from New Mexico. This is very broad theoretical input that is really essential for this. My former colleagues at the University of Montreal, there's still a very active collaboration. Some of the Raman data, I don't know that I'll show it, but it's very much in the context of what I will show. And really, everything that very importantly, everything that I will present today is very closely tied to structural information. So we know the structure of these materials down to very low temperatures. And that's very important because everything that we draw upon requires us to know what the structure is. And you will not see that explicitly, but it's a very important underlying bit of information in everything that I will talk about. So that's in the group of Chechare Sochi in Singapore. And this work is funded by the NSF. And these are the materials. This is the context of my talk today. These are these Ruddleston-Popper metal halides. I will talk exclusively today about this material that I have here. This is from this crystal structure, of course. And what these are lead iodide in our case, lead iodide layers. If you have a metal halide perovskite, a three-dimensional structure, and you just take one of these lattice planes, chop it up, separate it from the next lattice plane by these long cations, these long templating cations, you have a single layer of these corner-sharing octahedra, a single, there we go, single corner-sharing octahedra layer of these metal halide lattices, right? So you've got a single lead iodide layer, long cations, essentially vacuum, another layer, long cations. It looks like a multiple quantum well, like a very, very thin multiple quantum well in composite semiconductors like gallium arsenide. But there's something very different about those materials. One is the layers are very thin, these single octahedral layers, so you get very strong quantum confinement effects, And there's also a very high contrast of the dielectric environment between the lead iodide layer and what's in between, essentially vacuum with these organic cations in very low density, essentially, 1 per unit cell. And so you end up with very strong dielectric confinement as well. So that's a very important concept. It has very important consequences in the optical properties. In gallium arsenide, for example, in volume, in bulk gallium arsenide, exciton binding energies are milli-electron volts. You go to quantum wells, very thin quantum wells, and they will go to maybe 16 milli-electron volts, 16.16. So this is quantum confinement. Electron and hole have very strong interactions that the screening of those interactions is lower, but also there's a quantum confinement. There's a density of states effect and going to 2 dimensions, quantum confinement. Whereas in these materials, you have very strong quantum confinement effect, the 2-dimensional density of states, but you also have very strong dielectric confinement. The electron and the hole, because of vacuum around the single layer, have very, very strong Coulomb interactions. So in bulk, lead iodide, perovskite, hybrid perovskite derivatives, you have exciton binding energies of the order of kT at room temperature, somewhere between 20 to 40 milli-electron volts, around there. Whereas in these 2-dimensional materials, exciton binding energies go to 250 milli-electron volts, very strong effects. So you have very strongly bound excitons that are manifested in the optical properties. So here what we have is the absorption spectrum, and this is at room temperature of this very material. And this would be a relatively thick polycrystalline sample. I don't know, 100 nanometers or so. For us, that's thick. And you have features here. This is just the continuum absorption, the band-to-band absorption. But down from the band edge, you've got this what appears to be at room temperature, very well-defined resonance, and that's your exciton. That's the optical signature of excitons. What are excitons? They're Coulomb-bound electron-hole pairs. In the regime that we're talking about, Coulomb-bound electron-hole pairs, you excite an electron from the valence band to the conduction band. You leave behind a hole. There's very strong Coulomb interactions that give rise to bound states, hydrogenic-like bound states. And here's the origin of that series, right? And so that Rydberg-like series. And so these are very strongly bound excitons. The energy that it takes from separating electron and hole to free carriers, 200, 250 millielectron volts. That's a high binding energy. That's about 10 times kT at room temperature. So very, very strongly excitonic system. And so you've got this very, very well-defined resonance. You've got this photoluminescent spectrum, which reflects that as well. And the whole context of my talk is going to be on what the nature of these excitonic states are. And the reason for that is, the reason why that's interesting is that these materials are, in this way, very analogous to classic composite semiconductor quantum confined structures like quantum wells. But the systems, of course, optically are very different. In the sense, if you take bulk lead iodide perovskite derivatives and you measure the frequency-dependent permittivity function, you find that there's a difference between the static limit and the high-frequency limit of something like 100 or a few hundred. Whereas in gallium arsenide, it's a factor of 10 or so, maybe a few tens. And so this tells you that it's a highly dynamic system. It's an ionic crystal. It's a very highly dynamic system. Lattice vibrations are going to be very important. They're going to play a very important role in the optical properties as well as electronic properties, thermal transport, and so on. And to what extent are this very highly dynamic, noisy environment important in defining the nature of the fundamental quasi-particles that give rise to the optical properties? So that's a very important issue because I'm going to show you that both charges, polarons, what Esteban has very nicely shown us that I will present. Polarons, charges, photocarriers, are polaronic. They're very strongly dressed by the lattice in a regime that is very different from gallium arsenide, very different from very soft materials like the other class of materials that we work with, organic semiconductors. We're in some regime that is intermediate, that is very difficult to describe quantitatively. And so that's a context. Can we find ways to unifying exciton and polaron theories from very long delocalized weak coupling limits, the so-called Froelich limit of, let's say, gallium arsenide, to polythiophene in organic materials. And so we're in some intermediate regime, and to really develop a quantitative understanding of that requires us to really produce the kind of phenomena that I'm going to show today. That's a general context. So what I'm going to do is now show you, talk a little bit about the linear absorption spectrum, then I'm going to go more deeply into nonlinear ultrafast spectroscopy to really understand the spectral structure more profoundly. So here what I have, I showed you in the previous slide. This is the absorption spectrum over a rather large spectral range. At room temperature, you see your nice resonance, your exciton. You cool it. Here this is, I believe, at 30 Kelvin. And at 30 Kelvin, what you see is that you've got some spectral structure. You don't have one peak, but you have here, when I plot this in a log normal scale, you have at least 4 peaks. And this is not a new observation. This is something that has been reported since the 1990s when people, the previous, let's say, incarnation of this field was very much interested in these materials. You notice that there's spectral structure, and that spectral structure seems to be quite universal, quite general in these materials. What you see is that here's your main exciton peak for no good reason. We're going to call it XA. That has nothing to do with any symmetry label or anything. It's just, Jack and Jill. XA and XB are 2 main exciton peaks. So XA will be this one, the main one. But you see another peak here at 35 millielectron volts away. Then there's another one at 35 millielectron volts away, one at lower energy, 35 millielectron volts. So there's this very even spacing. And that seems to be something rather mesoscopic, because if I changed iodide to bromide, you still get your 35 millielectron volts. So the weight of these might change, the structure will slightly change, the details of the line shape will change, but it's about 35, 40 millielectron volts. You change lead to tin, get about 35 millielectron volts. You change the phenylethylammonium ligand to something else, same thing. You put 2 layers, 3 layers, 4 layers, 5 layers of lead iodide, 35, 40 millielectron volt line spacing. And so if you're a chemist, you think this really looks like something we really understand. In molecules, you've got very strong coupling of the electronic degrees of freedom with local vibrations, electron vibrational coupling that gives rise to bibronic progressions. You have you've got an origin by bibronic transition, the coupled electronic vibrational transition, but then you have like overtones. You have vibronic replica that give rise to a series with energy spacing that tells you what are the vibrational modes that couple to the system. You do that type of analysis here, and it really doesn't work out. You find ways in which it might, because you might get combination of vibrational modes, but it doesn't quite work out. And so what is the origin of this line shape? Now, the reason why this is important in our group, and Victoria is sitting here in the front, one of the things we're interested in are optical microcavities and strong exciton-photon coupling. And let's say that Victoria goes and makes a very nice microcavity, and we're interested in understanding the relaxation of electron-hole into this quasi-particle that it's a strongly coupled photon, exciton. How do these scatter off each other? How do these populate the new ground state formed in this new system to form things like Bose-Einstein condensates? And so scattering is very important. How does this spectral structure, the origin of this spectral structure, have consequences in that kind of scenario? That would be the context of why we're interested in these systems. And so what is the origin of this complex line shape that I am describing here? And really, the bibronic progression has been one that seems like a natural explanation. There are other very convincing explanations of there being spin exchange reasons for that. But we could not understand why from those types of models, why you would end up with 4 transitions. So we started thinking about this, and we said, what if, we know that in bulk perovskite, bulk lead iodide perovskite, you have very strong polaronic effects. The charge, because it's such an ionic and dynamic system, the photocarrier is strongly bound to the lattice via phonons, via phonons, and that dressed photocarrier will have the consequences on the charge transport are going to be important. These materials are known to have, although very long carrier lifetimes, relatively limited mobility, and so it has been thought that, and really has been sort of understood, that polaronic effects are important. What's a polaron? It's a charge that is very strongly coupled to the lattice in the regime of gallium arsenide through just phonons. So the lattice motion, the charge perceives the lattice through the motion of the phonon, through the lattice motion. In a small polaron limit, like in organics, you've got a very strong local coupling to a vibration that deforms the lattice around you. And so somewhere in between, that's what's happening here. But now we've got an electron and a hole that are interacting. That electron and a hole individually may be dressed by the lattice, not necessarily in the same way. And then all of the interactions, all of the Coulomb correlations between an electron and a hole contain all of the couplings of each carrier to the lattice, so that the quasi-particle is really a composite exciton and polaron, a so-called exciton-polaron. And so the exciton-polaron hypothesis was sort of first formulated in our minds, and we thought, well, what if you have diverse correlations between, let's say, polaron-polaron, untrapped carrier, polaron, untrapped carrier, carrier. Now that's a simplistic way of looking about it, but that was the idea. So how do you test that? That's the Exciton Polarons perspective. So there's a perspective article here in which we highlight all the phenomena that I'm going to show you right now. Not all. I'm not going to go through all of it, but that would be a summary of what the logic was behind this hypothesis. So in order to really also participate in the development of methods, not as directly, but sort of through our colleagues, electronic structure calculation methods that really take into account all of these interactions, one would have to really look at this. And that was another general context. So you're a spectroscopist, and so you say, okay, if I'm saying that this exciton here has a different lattice dressing, it perceives the lattice motion differently than this one, what I need to do is do a resonance Raman experiment. In a resonance Raman experiment, you would excite with a laser that's in resonant with an optical transition, either XA or XB. And so you tune your laser to be here or to be here, and then you measure the Raman spectrum, and really the modes that are coupled strongly to the electronic transition are the ones that have high Raman cross-section. So the Raman spectrum that you see are the modes that are coupled to that electronic transition in resonance Raman. And the amplitude, the amplitude of the Raman peak tells you to what degree are those modes coupled. Okay, so that's the information that we're after. So we go off and do that, but we don't do that in the frequency domain. We do that in the time domain. Let me not go through all of this too carefully. Let me skip the theoretical argument here, and let me just go to the experiment. You excite. We do this in the time domain. The experiment that I'm going to show you right now is you excite with a short pulse, a femtosecond pulse, and then you do a pump probe experiment. You pump with a femtosecond pulse, then you take another white light probe, femtosecond probe, you transmit that through the sample, and you measure the changes in transmission induced by your optical pump. You've removed population from your ground state. You go from a valence band to a conduction band. You bleach away the valence band, and you see that through a change in transmission of the probe. So that's the experiment. But now if you've got a system in which the electrons are coupled strongly to phonons, you impulsively excite the electrons. You inject electrons in the conduction band impulsively. That's like you've got a pendulum, an oscillator. You hit it very quickly and very hard with a hammer, but you don't hit one. You've had the ensemble of pendula that you hit very rapidly, very, very impulsively with a hammer, and they all start oscillating in phase. So you excite, you inject electron in the conduction band. These are coupled to phonons. All the lattice starts ringing with the phase of the electric, that you impose with your femtosecond pulse. And so all of these oscillators in phase. You essentially form these vibrational wave packets that are oscillating in the ground state, and your time-dependent transition probability will be modulated by this vibrational wave packet oscillating in the ground state. So what you get are a transient absorption spectrum. Here we have, this is your ground state absorption spectrum. This is at 5 Kelvin. And you pump the photocarrier, so you pump at high energy. You're injecting electrons into the conduction band. You're not exciting yet here, the excitons resonantly, but you're just injecting electrons in the conduction band. And you get here in the region of your ground state exciton absorption, this transient transmission spectrum. And it's complex because you pump, you move electrons from conduction band to valence band to conduction band. There's changes in the permittivity function and so on. You get shifts, and you get a complex line shape. And so at the moment, let's not worry about that. But we notice that on top of the line shape, you get these oscillatory components. You get these wiggles, and that's what's called a resonant impulsive stimulated Raman response. So you get these wiggles. You throw away the dynamics. Let's not worry about what the population is doing, the electronic population, and so you just retain the wiggles. Here they are. You've got this oscillatory response. There's sort of right at the peak of this exciton, XA. You've got a phase shift. These are classic signatures of resonant impulsive stimulated Raman spectrum. And so that's the signal that you measure. Then you take the signal. So here it is. You take a cut along a particular probe wavelength, and you have this oscillatory response. You see this ringing. You see several modes. There's a strong temperature dependence. That's what Esteban is going to tell us a little bit about in a moment. But let's look at 5 Kelvin. You've got this ringing response. This is just a Raman spectrum in the time domain. You can Fourier transform it, and this is basically a resonance Raman spectrum. And so this resonance Raman spectrum is decomposed into various modes that have a relative intensity, and this is just a labeling, M1, M2, M3, M4, and so on. And so these modes, the intensity of these modes tell us there's a phonon that couples to the photocarrier, and the degree of coupling is represented by the amplitude of this. Very strongly coupled phonon will have very high amplitude. If it's a Raman allowed vibration, it will have very high amplitude in the Raman spectrum, whereas this one has much lower amplitude. It's coupled much more weakly to the photocarriers, right? And so you've got your spectrum. It's very clear, very well defined, very sharp peaks, and you can do various means. You can either do a measurement where if you had a very nice single crystal, you could do polarization measurements to really measure the Raman tensor, or you go to your friends and your colleagues and say, just with relatively standard nowadays ab initio methods, can you assign these modes? That's what these are. These come from just ab initio calculations of the system, and so we know that these are all lead iodide and the lead iodide plane modes that involve some sort of rocking as well as twisting of the octahedral units. This M6, which is this one over here, has slight out-of-plane motion as well of the octahedral. So all in the lead iodide plane, M6 a little bit out of plane, and that's going to be important in some of the data that Esteban is going to show us in a minute. And so here we have it's a Raman spectrum. We know what the phonon modes are, at least by comparison with the ab initio calculations. We can assign it, and we know to what extent these couple to photocarriers, and what else can they tell us? Now we go off and do the experiment, the same experiment. So let's remember this spectrum here. You know, this is a spectrum of the resonant impulsive stimulated Raman injecting photocarriers. But now let's do the experiment. Let's tune our laser to XA and then to XB. Now let's look at the excitons. We expect that if it's a vibronic progression, all of these features are replica of the same electronic transition. They should reflect the same electron-phonon coupling as the origin of the transition. So now let's do that by pumping the different modes. And so now we go resonantly with XA. We still have this, what we called M2, that is dominant, but you notice that some of the amplitude of the lower frequency phonons is much lower. Okay, so this mode is still very centrally responsible for dressing the exciton, dressing coupling to XA and modulating that. And so that's still the case. But these much less so than for the photocarriers. Now we go resonantly with XB, and now we see that these relative intensities are very different. Now we still have this M2, but now these guys are very important in the dressing of the exciton B, as well as these. Okay, so now we take these amplitudes, the relative amplitudes, and we plot. This is just a Mathematica sketch, but the energies in the relative displacement here are come from the measurements. We have a ground state. We have different excitons here, XA and XB, that are coupled differently to two different phonon modes here in this representation. These axes are like a displacement axis along some effective coordinate for each of these phonons. It's, let's say, project all of the motion into a single coordinate, and you would have these different plots. This is the energy of the excitons with respect to the ground state, and the displacement tells us we've excited to these exciton states, and there's a local lattice deformation. That's what that represents. There's a local lattice deformation that is different for exciton A and exciton B. So exciton A and exciton B are dressed by phonons in a very distinct way. They're not the same species. They're not the same optical transition. That doesn't show that they're exciton polarons. The other models that I talked about briefly are also, you would see this, but they are dressed, each of these excitons are dressed distinctly by the lattice and distinctly from the photocarriers. Okay, so this supports the exciton polaron story. You might have exciton polarons. We haven't proved it, but certainly this data is consistent with that. But what would be the consequence? It's very interesting to talk about these things, about the nature of the spectral line shape. Are they exciton polarons, spin exchange? There's relativistic effects, so-called Rashba effects. That's a very fascinating discussion. But so what? What are the consequences? Well, I've talked about scattering, and I'm going to talk about that further in a moment. But something I'm not going to show you is we've also shown that if you inject electron and hole into your semiconductor, they recombine. And at 5 Kelvin, electron and hole recombine into XB. Let's say you want to make an LED. You want to make a light-emitting diode. What is your emissive state? You inject electron hole. Within a picosecond at 5 Kelvin, they recombine into exciton B. Then they recombine into exciton B, and within tenths of picoseconds, they relax to exciton A. And that is a radiationless relaxation, a so-called non-adiabatic relaxation that produces the lowest exciton state. That's your emissive state in the LED. What is the mechanism? What are the role of these phonons in mixing exciton A and exciton B states to permit that radiationless transition from one state to the other, to produce your emissive state in your LED? Turns out that these phonons, M2 particularly, is not what we would call a spectator. It's not just that you've excited this phonon and it happens to couple, through the exciton, and it's coupled, and then that's the end of the story. They're active in driving the electronic relaxation from exciton A and exciton B. That's a very important consequence of the fact that they're exciton polarons. Okay, that character would very strongly impart the relaxation, the electronic dynamics in the system. So that's one story I'm not going to show you, but what I am going to show you is another experiment in which we're now going to the type of question that we're interested in for the optical microcavities. Let's say that we have an exciton here and there's an exciton there. If I'm in the microcavity, we're going to couple strongly to the photon to form so-called Exciton-Polarons. We're going to scatter and exchange momentum, and that feeds a ground state, a new ground state that is at a particular density, below a particular temperature. It's going to form something akin to a Bose-Einstein condensate, perhaps not in equilibrium, but it's going to be something like a condensate. Okay, so the mechanism for that is exciton scattering. Now, if I'm exciton A and my colleague there is exciton B, we perceive the lattice in a very different way. How does the fact that we're dressed by the lattice differently affect the scattering? So that's what we're going to focus on right now. To do that, we use another experiment that is a nonlinear optical spectroscopy, in which we're going to essentially measure something like a photon echo, but we're going to spectrally resolve it. So in this experiment, we bring in a sequence of femtosecond pulses in some well-defined geometry. Let's say we make a square and we put 4 pulses in the square. There's 3 of them that are going to be the ones that are going to produce the signal. There's another one here that is going to just be an experimental trick to be able to measure both the amplitude and phase of the signal. But let me describe the experiment this way. And you really don't need to understand very much other than what I'm going to say at the very end of this explanation. And let's say that you bring in 3 pulses, you put them A, B, and C in the corner of this box. You focus them on your sample, and there's some time delay between each of these. The first pulse, and let's just think of this classically. First pulse is going to see the electrons in the bulk in your sample. It's a femtosecond pulse. It has an electric field profile. That electric field is going to start driving the electrons, the oscillators, in phase. It's a very short pulse. The electric field is very well defined. It's going to start driving all the electrons in phase, and they're going to start oscillating. But then they're going to, either because they're very strongly coupled to phonons, or because of the scattering. If I'm an electron here, there's one there, we feel each other coulombically, that's going to scramble our phase. So there's a dephasing process, so-called dephasing. But before that happens, before we dissipate this phase, we come in with another femtosecond pulse. And our first one set up this oscillation, and it all adds up, and it's a macroscopic polarization that is coherent. And it's coherent macroscopic polarization, all in phase, well-defined phase. In comes the second pulse after some delay, but we haven't dissipated the coherence induced by the first pulse, and it drives the system further. It keeps driving these electrons further. But now you've got an angle between the two because you had one in A and one in B. There's an angle. And so you set up some interference pattern. You set up a grading of this macroscopic polarization. So this polarization grading. Before that dissipates, you come in with your third pulse, pulse C, and it keeps driving the system. But now it sees this periodicity of this coherent polarization grading, self-scatters into a direction that is right at the corner of this. You mix it with another replica pulse, you interfere it in your detector, and you have a way of measuring the amplitude and phase of this coherent response of the sample. So you measure a third order, essentially a signal that is proportional to third order susceptibility. It's a nonlinear experiment. And that has a lot of information on the structure, the optical structure of the sample. So you measure, you detect here the amplitude and phase of that coherent emission. Maxwell tells you you've got a time varying, you've got a polarization with a non-zero second derivative. This should emit. You have emission, you detect it here, and you measure the amplitude and phase of that. And that's one energy axis, right? But now you also scan the delay between your first two pulses, which is a coherent response, which is in the time domain, your electronic spectrum as well. So you Fourier transform that, and now you've got a two-dimensional spectrum of, let's say, an excitation axis, that's this, and a detection axis, what you measure at the end, okay? So it's a two-dimensional, you don't have amplitude versus energy, you've got amplitude versus energy versus energy. But these two energy axes, because it's a coherent experiment, contain correlations. Exciton A and exciton B are correlated. There should be a cross peak between these two energies. So that's an important thing that I'm going to show you in a minute. But importantly, this is a bit where you really need to understand what the value of the experiment is. If I measure an absorption spectrum, I see a certain line width. And I can't tell you uniquely what is the contribution of that line width from the fact that there's heterogeneity in the sample, there's disorder, there's one exciton here at a different energy than there because of polycrystallinity and whatever, and the homogeneous line width, which contains the fundamental content of the optical transition, this dephasing process that I've talked about, right? I can't tell you that from a linear experiment. But here, I can analyze this 2D line shape to isolate the homogeneous and inhomogeneous contribution, which means that if I can isolate the homogeneous line width, I can tell you what the dephasing dynamics are. I also measure them through the time domain. But I can spectrally tell you what the dephasing time is. And from the dephasing time, I can tell you, now let's change the density so that they're scattering. And how does that affect the dephasing? And importantly, how is that dephasing differently for XA and XB? And why? How do these phonons that couple to the different excitons, how are they responsible for differences in the scattering rate? And so that's what we're going to try to address here. So here's a measurement of this two-dimensional line shape. Here we had, this is a much thinner sample than before. You see that these exciton resonances are much better defined. Here's one, here's XB. There's other things that we make out with this thinner, better result sample. But you see that you see these peaks in this two-dimensional spectrum. Here in the diagonal, you see these features, as you should. You see that XA and XB have cross peaks. It's not like in the sample There's a region that has exciton A and another region that has exciton B because it's a messy sample. These are fundamentally part of the electronic structure. They're cross peaks that are correlations between these. They share common ground states. So these are fundamentally part of the optical structure of the sample. So that's nice to show. We also see features here which are biexcitons. We can measure biexcitons. Biexciton binding energies are different for XA and XB. I'm not going to talk about this, but that's something else that is a consequence of the lattice. But we see this spectrum. And we can analyze the line shape to separate homogeneous and inhomogeneous contributions through a line shape analysis. Won't get into the details, but that's the exercise here. So you do that, and you can measure dephasing, and that dephasing is going to depend on two things. There's going to be a low density limit where there will be a certain dephasing that will change between this sample or that sample or Daniele's sample and Esteban's sample, or it got shipped by UPS from Milan packed in a prosciutto bag, but something went wrong. Literally, that's how they sent it to us. But something went wrong in Atlanta winter or summer, humidity and so on. So you get a different sample, and your dephasing that will be at your low density limit is going to be different because the defect density is going to be different, and scattering sources are going to be different. But let's say that that's your gamma zero. But then there will be a part that will depend on density, exciton density. You crank up your laser power, you inject more excitons, and your density increases, and there will be a linear component, linear dependence on density. So it's a gamma zero plus, let's call it a delta times n being the density. So you do that, and then you notice that your low density dephasing is measurably different between XA and XB. So already the fact that the excitons are dressed differently by the lattice mean that they're protected in a different way to elastic scattering. Okay? But then when you increase the density, you also find that the density dependence is measurably different for XA and XB. Then this thing in between, which is XA prime, it's a very mysterious thing to us at the moment. But you see that that's also very different. And so there's two things that I want to say. If you look at these deltas, if you measure the deltas for this sample, and then let's take another two-dimensional system that is also very interesting and relevant for the same applications that I talked about, but very different character. Let's say a transitional metal dichalcogenide, which is just a fully covalent, single-layer, two-dimensional semiconductor. You have the same quantum confinement and dielectric confinement effects, but it's a covalent system, right? And so if I measure these deltas for molybdenum diselenide, I find that there's a difference of about 100 to 1,000 in the scattering rate, in the density-dependent scattering rate, what's called excitation-induced dephasing. And that is because here you have a very strong effect of the polaronic protection. The lattice protects, imagine a bowling ball that either you roll down in a bowling alley and it goes down the lane and it does its thing, or you put it in your mattress and you roll it down and it's, it deforms the mattress around it that sort of protects it, right? And so this is the bowling ball in the mattress. The molybdenum diselenide is a bowling ball in the bowling alley. And so there is a very strong consequence of this polaronic protection on the scattering rate. That will be very important for the formation of the Bose-Einstein condensates, for example. And so you've got differences in factor of 100 to 1,000 of the scattering rates, but the scattering rates for exciton A and exciton B are not the same, which is the one that is going to feed your condensate. That's going to be a very relevant question. And so how should Victoria design her microcavity to optimize XA or XB, right? And so that's important. So you get also a lot of information through line shapes. you get, without really getting into too much detail, because now we're starting to get into the more involved nonlinear spectroscopy, but the line shape has signatures that are very clear signatures of this excitation-induced dephasing at very early time. You measure the real and imaginary components of your spectrum, essentially of your permittivity function, and you should expect an absorptive and dispersive part, but they're mixed because of this nonlinear many-body interactions, and when that dissipates, because the scattering rate is very important, at early time you wait a few, to us a very long time, a few hundred femtoseconds, and all of a sudden you no longer feel all of these Coulomb interactions, and now your line shape looks like you would expect from the textbook. And so that's important. But you also get information. Let's see, I think I want to, you still get information on the dynamics of the scattering if you look at, for example, the line width, the homogeneous line width. So the dephasing, the initial dephasing, this is for XA and this is for XB. This, you notice these start at 0 femtoseconds and they end up in 350 femtoseconds. So your initial 0 at this particular density, your gamma 0 for XA and XB is very different. So very different dephasing to begin with because of this polaronic protection from exciton-exciton scattering. But as normally happens in these experiments, you excite, you generate some population, and then you have spectral diffusion, things diffuse. You start out from a narrow distribution of states that you create optically, and then these evolve to a broader distribution of states. You should get spectral enlarging. But here what you get is narrowing, because here at early time, the many-body scattering gives you the spectral broadening, this increased dephasing process. As that dissipates and this narrows, and from the dynamics of the I'm getting a lot of emails here, from the dynamics of this line shape, of this line width, then you get something about the excitation-induced dephasing dynamics. So that's the kind of things that you learn. But the bottom line is they're different for XA and XB. So now I'm going to wrap it up. You can also do temperature dependence. And again, the temperature dependence is different for XA and XB. What is the thermal dephasing mechanism for your excitons? Your excitons have this mesoscopic phase, but now they couple to phonons. There's this exciton that couples to a phonon at a different point in the period to this other exciton. That's a dephasing mechanism. And so as you populate phonons with temperature, you would expect a thermal dephasing, and that you see that that's different for XA and XB. And you can analyze that, and I'm not going to have time to get into Esteban's work, unfortunately, but I'm going to let me just give you the gist of it, is that the question is, why are certain phonons more important in dephasing than others? Why do certain phonons that couple differently to XA and XB more relevant in preventing or enhancing exciton-exciton scattering? Why are certain phonons preferentially the ones that mix exciton A and exciton B to non-adiabatically relax from one exciton state to the other exciton state? And we need to understand the nature of the phonon-phonon interactions. This is where Esteban comes in, and he does not a Fourier transform of our oscillatory response, but rather a wavelet transform. And now if you want to really know the details, you have the expert here rather than me. But what you show is that if you take this data that we used to measure the resonant impulsive stimulated Raman spectrum, but you don't do a Fourier transform, you do a wavelet transform, you get not just the intensity spectrum, but the time dependence. And so what you notice is that there's a phonon here. This is M2, the one that happened to non-adiabatically mix, the most important one in protecting excitons against scattering, carriers against scattering as well, that is highly temperature dependent. That is phonon and Here, what we're doing is we're back to not just injecting photocarriers, and we're looking at the phonon coherence, the amplitude of this phonon coherence that we generate impulsively as a function of time at different temperatures. And this M2 phonon has a very strong temperature dependence because it's a highly anharmonic phonon. In order to get phonon-phonon interactions, you need anharmonicity. There's this other phonon here that is not very strongly temperature dependent, not very anharmonic. This guy is responsible for many of the population as well as the quantum dynamics that I've shown you. This is really a culprit of a lot of the optical process that I've shown you. This one sort of participates as well, but to a lesser extent. And so what we see here, if you look at the temperature dependence of the coherent response from this vibrational spectroscopy, this is M2, the one that really dominates. It's highly temperature dependent, you can model it. In a minute I'll show you how. This one is not very highly temperature dependent. It's rather temperature independent. This one has slightly more out of plane motion than this one, and that could be one reason why that's the case. But you can sort of model this as you generate an optical phonon because you've excited your carriers in the semiconductor, that you have a parametric conversion between that and acoustic phonons, and it's a nonlinear process, and you can quantify the nonlinearity by looking at this anharmonicity parameter. And so that's a very important quantitative input, and I don't have time to get more into that. There's quite a bit more to say. But what I want to do right now, because we're about to run out of time, is that this phonon anharmonicity is central in the way that phonons dress excitons and carriers, and what are the consequences dynamically of these excitons. Okay, so we have spectral structure that is due to, in our opinion, I'm not going to get into this. You can also, this is Ajay's data, it's not our data, so let me just skip it. But what we know so far, there are phonons that are highly anharmonic that happen to dress excitons, XA and XB differently, and we believe that this is the source, an important part of the source of this spectral structure. And that's something that has to be described quantitatively by state-of-the-art first principle calculations. And that's not trivial by any means. That's a very challenging problem. What the consequences of these are that whatever the population and quantum dynamics are very much modulated by the details of how these phonons couple to the different excitons or to photocarriers, and what the differences are in this fine structure that we see. So I leave you with the conclusions that I've touched upon throughout the talk, but really we do think of excitons into the hybrid metal-halide perovskites as exciton polarons, and this has very important consequences in that these are not excitons as we know in a very clean regime like in multiple quantum wells of, let's say, 3-5s. They're not excitons in a very strongly localized and confined regime like so-called Frankel excitons, Rashba-Pecker polarons in let's say in an organic crystal. But these are in a very interesting intermediate regime, and I would say that this is one of the open issues in exciton physics. How do we describe things bridging one regime to the other? And that's the subject of my current NSF proposal. So with that, thank you very much for your attention and for the invitation. I'm very happy to have presented this today.
Okay, I think we have time for maybe one or two quick questions. If anybody in the audience here has a question, I'll pass the mic to them. All the way, of course, all the way at the back.
Thank you. So I guess I actually have maybe a two-part question.
Yes.
The first part is, if money were no object, and there was a characterization tool or ability that is lacking, like what would you like to have that would help you get to the next level?
Yes. What I would love to have is a time-resolved structural probe, and we have begun to collaborate with certain colleagues, but there's some challenges that we're still trying to overcome. One of them is time-resolved electron diffraction. So we would like to see, as we're undergoing the kind of dynamics that we're probing with the experiments that I did show you, what are the lattice dynamics as well? A time-resolved structural probe with sufficient time resolution to look at the dynamics that I'm looking at here would be highly valuable. That would be my top choice.
And the follow-up to that, if money was an object, like, is there low-hanging fruit that you would also like to have that is currently lacking?
Well, the low-hanging fruit are the kind of things that we've done that we really want to extend to many different systems. Now that we're fortunate to have a world-class chemist and a physicist in the group, now we have the opportunity to look at a range of materials. And I think that's a low-hanging fruit, is to really be able to walk around the materials parameter space doing the kind of time-resolved Raman spectroscopy that we do. And that's a focus. But really, what I hope I portrayed is that what you need is really a combination of everything from linear spectroscopy to these more complicated nonlinear spectroscopies to develop kind of a general broad picture. Now we need to do this for a range of materials to really expand the story. And so it's not a low-hanging fruit in terms of let's just do a couple of experiments and we've learned a lot more, but there is kind of the framework for us to really walk around in a broad parameter space that I think is what's required.
I think in light of the hour, I think we're going to conclude now. Let's give Professor Silva a round of applause one more time.
Thank you.
And we'll see you all in about 2 weeks on October 25th, the next seminar. Thanks.